Hello and welcome dear students. Assalamu alaikum to everyone. My name is Gauhar Nabi, your mathematics educator. Today, the topic that I am to discuss with you is one of the most important topic. It is something which is going to be very interesting. The topic is regarding why can't polynomial functions have a fractional or negative degree, right? So it means that we have polynomial functions, we have polynomials. So why the degree of polynomial can't be fractional number? Why the degree of polynomial can't be negative number? Is it necessary? Because as a mathematics educator, behind everything there's a reason. So you need to find out that very reason. If you are raising the questions in class 9th, class 10th, class 11th, class 12th, mostly in class 9th or 10th, because student is only limited up to the definition of polynomial. This is the definition of polynomial and these are the questions that we are told to solve. But what about if we delve deep into the definition? If we focus too much, if we logically think about the definition, is it necessary that we impose the restrictions over the polynomial functions that the degree can't be negative or degree can't be fractional number? क्या होगा? कौन सा पहाड़ टूट पड़ेगा अगर ये डिग्री हो भी सकती है, right? So this is what I'm going to we are going to discuss today. Why degree can't be negative number? Why degree can't be a fractional number? Okay. So before discussing this, let us have a look over the general form of the polynomials. What is the general form of the polynomial function? If you have to write down the general form of the polynomial function, the general form of the polynomial function is p of x equals to a n x raised to power n plus a n minus 1 x raised to power n minus 1 plus so on to plus a1 x raised to power n plus a naught x naught. Now it depends upon these powers n minus 1. So it can be clearly seen that these are whole numbers. These powers are these exponents are whole numbers. These are not these are neither fractions nor any negative number, right? So this is the general form of the polynomial function. So it depends. Whenever we replace this n by 1, okay, it will become linear. Whenever we replace this n by 2, it will become quadratic. Whenever we replace this power by 3, it will become cubic. Whenever it represented by 4, it will become biquadratic. So all the polynomials can be generated from this general form of the polynomial function, right? So, but our task is to prove why can't the degree of polynomial function be fractional, not either fractional number or negative number. This is what I am to prove today. So, in order to define this thing, we have to understand that whenever a student is in class 9th, whenever the student is in class 10th, right, he's limited up to the definition of the polynomial, but he unknowingly, unintentionally, the student is playing with the functions. Polynomial is nothing but it is the function. Polynomial is nothing but it is the function. But what is the function? Function is the rule, or we can say the set of rules, right? So in which the set of inputs are there and set of outputs are there. So corresponding to each input, we will get an output. But that output, it should be unique. The output should be unique. Uniqueness should be there. Right? So, but whenever the polynomial is a function, every polynomial is function. That's why we call polynomials as polynomial functions in class 11th. Whenever student is in class 11th. They call it polynomial function, right? These are polynomial functions. But what is the beauty of these polynomial functions? The beauty of these polynomial functions are that polynomial functions are everywhere continuous. But this is one of the mathematical I would say the continuity. It is the one of the mathematical concept continuity, that all polynomials are continuous everywhere. So what does this mean, that all polynomials are continuous everywhere? It means that there must not be, graphically we can say, there must not be any breakdown in the graph of the function. Or whenever we are in a position to draw the graph of the function without lifting the pen of the paper, it means that, here in this case, without lifting the pen of the paper, it means that we are dealing with the continuous functions. The graph of the function is continuous. The graph of the function is continuous. So this is what we can interpret geometrically. This is what we can interpret graphically, right? That polynomials are functions, but these are special type of functions. What special type of functions are these? They are continuous functions. They are continuous everywhere. That we can draw the graph of these. We can draw the graph of polynomial functions without lifting the pen of the paper. This is the graphical interpretation. But now next, this is the polynomial, that polynomials are functions, special type of functions. They satisfy the property of continuity. Not only this, polynomial functions not only satisfy the property of continuity, it also satisfies the property of differentiability. So what do we mean by differentiability? What is the graphical interpretation? I'm not going to write down the in terms of the letters, that f of x tends to a, f of x tends to f of a, or whenever x tends to a. I will simply present. I'm here to present the graphical interpretation of the polynomials. So if a polynomial function is continuous and differentiable, we got this concept that polynomial functions are continuous. But when can we say a polynomial function is differentiable everywhere? So when can we say geometrically that a polynomial function is differentiable? A polynomial function is differentiable whenever the graph of the function is smooth, whenever there is no cusp. Cusp means there must not be any edge. We will discuss it one by one with the help of some graphs that I have written down, that I have inscribed on the board, right? Okay. So now we will take an example of the linear polynomial. What is linear polynomial? Linear polynomial. This is the linear polynomial y equals to f of x equals x. This is the linear polynomial function. Why this is called linear polynomial function? Because algebraically its degree is 1 and its graph is a straight line. This is the linear. From the word linear, we mean that graph is straight line. Graph is straight line. So this is the linear polynomial. This is the type of a polynomial. We call it linear polynomial, right? And what is the beauty of this linear polynomial? That this linear polynomial is continuous everywhere. So from continuity, what we can conclude? From continuity, we mean that if we take any point from the domain set, this is the domain set, x is represented by domain set. Whenever if we take any point from the domain set, and corresponding to that point in the domain set, whenever we apply f on that very point, we get an image here on this graph, right? So corresponding to each x, we get f of x on this graph. So graph of the function is nothing, but it represents the range set. It represents the range of the function, right? So it is continuous. Because why continuous? Whenever we take this pen and we draw the graph of this function without lifting the pen of the paper. Without lifting the pen of the paper. I mean to say, हमें जरूरत नहीं पड़ रही है कि हम पेन को किसी भी point of time पे उठाएं. This is what I mean. This is what continuity implies graphically, right? So, but this is not only continuous, this is also differentiable. How this is differentiable? Differentiable in what sense? That at every point, differentiability implies the slope. It gives the measurement of the slope. It gives the concept of the slope, right? Slope of the tangent line. Slope of the tangent line. At every point, wherever we want, we can draw easily a slope. We can draw easily a tangent. Tangent can be drawn at every point on this graph, right? Tangent can be drawn, and the graph of this linear function is smooth. So it means that this is the linear polynomial. This linear polynomial is a function. How it is the function? It is the function that we can also show it by the vertical line test. Vertical line test, that if we have to prove whether the given relation is the function or not, we can apply the vertical line test. We can here use the vertical line test. From vertical line test, we mean that it is a function. It is a function. It means that corresponding to every point from the domain set, there exists an image. Corresponding to this point, there exists an image. This is what we mean function. So, right. So this linear function, this linear polynomial is a function. It is continuous. It is differentiable. Now moving back to the another topic, the another polynomial, that is the graph of this polynomial is this is the graph of constant polynomial, right? So what is the constant polynomial? Y equals to f of x equals 2. So whatever the value we replace by this x, we again and again in output, in range set, we will get only this 2. Okay? And this is the graph of the constant polynomial. So what is the beauty of this constant polynomial? This constant polynomial, if all polynomials are continuous everywhere, then constant polynomial, it is one of the type of the polynomial. So this constant polynomial is also continuous everywhere, right? And it is differentiable everywhere. How this is continuous everywhere? This is continuous everywhere. That, see, if we start from this point graphically, and we can draw the graph of this constant polynomial without lifting the pen of the paper. From this point to this point. Okay, so this proves the continuity. Now next is the differentiability. How the constant polynomial is differentiable graphically, we can say. As we can see that the graph of the function is smooth. Not only smooth, and there is no cusp. Cusp means there is no edge in the graph, and there is no hole in the graph. So it implies that it is differentiable. Not only this, at every point we can draw tangent. At every point we can draw tangent. So from this we can also conclude that at every point we can draw tangent. But it is another thing that the direction of the tangent, it is not changing. The direction of the tangent is same. It implies that the curvature is 0. So whenever there is curvature, whenever curvature is 0, it means that the curve is a straight path. So this is the straight path. So this is the constant polynomial. It is function by what? Function by vertical line test. Right? So corresponding to each input, there exists an output on the graph. Corresponding to this input, there exists an output here. Corresponding to this input, there exists an output here. So corresponding to each input, we get an output. And what's the beauty of those very outputs? They are unique. Unique in what sense? Unique In what sense? Uniqueness is there, which makes this relation a function. Continuous function and differentiable function. Now we have moving back to the next graph of the function. This graph is the graph of the quadratic polynomial. So what is the quadratic polynomial? Quadratic polynomial is it's a type of polynomial which is in the form ax square plus bx plus c, right? And the mouth of this quadratic polynomial, it opens upwards. It means that the coefficient of this x square is greater than 0, right? So this is a function. This is a function. How this is a function? By vertical line test. Draw the vertical lines. If the graph it were like this, if the graph of this function were like this, and we draw the vertical line tests, and this is the x-axis, this is the x-axis, and this is the y-axis. But here what we can observe, corresponding to this input, there exists an output here, and there exists another output. So it means that this is not a function. This is not the graph of a function. This can be a relation, but it's not a function. But here in this case, it is the function. How? Draw the vertical lines. Every vertical line touches the graph at a single point. This vertical line touches at this point. This vertical line touches at this point. Every vertical line touches the graph of this function at a single point. So here the case is totally different. Here the vertical line touches the graph at 2 points. This is the point 1 and this is the point 2. So it means here we can conclude that this is not the function, but in this case this is the function. This is the graph of the function. Okay. So now moving to the another topic, moving to the another curve, moving to the another graph of the function. This is the graph of the function, but this is the graph of the cubic function. And what is the beauty of this cubic function? This cubic function is a function from vertical line test. Not only this cubic function is also continuous. How this is continuous? That we will start from this point. We will start from this point graphically, and we can draw the graph of this function without lifting the pen off the paper. Without lifting the pen off the paper. Without lifting the pen off the board. Right? So it means that it is continuous. Now for differentiability, at every point we can draw tangent. We can draw tangent. Right? At every point we can draw tangent. So this implies that it's also differentiable, and there is no cusp. There is no edge in the graph, right? There is no edge in the graph. Now we have another. Let's take another example. Let's take another graph of a polynomial, the function. This is the graph. But from this graph, it can be clearly seen that this is discontinuous. This is not the graph of any polynomial function, right? This is not the graph of any polynomial function. Why? Because polynomials are initially functions. They are firstly functions, then they are continuous, and they are also differentiable. But in this case, it is discontinuous. There is point of discontinuity. There's breakdown in the graph. So it means that the graph of this function is not continuous. There's breakdown. Right? And second one, if it is not continuous, so how come it be, we can call it a differentiable function. So simply just keep this in mind. If a function is not continuous, it means that it is not differentiable. Right? It is not differentiable. If a function is not continuous, it means that it is not differentiable. But if a function is differentiable, it is necessary that very function, it must be continuous at that very point, right? So it is not neither a function, it is not a continuous, and it is not differentiable. Now let us move to the another graph of the function, which is most important as far as not only mathematics is concerned, but also the physics, from the perspective of physics. As far as the physics is concerned, we will take the graph of the function. We will take the law. Which law is this? It is Boyle's law. What it says? Boyle's law says that in physics, Boyle's law says that pressure is inversely proportional to volume. That means it means that as pressure increases, the volume decreases. Okay, so this is the Boyle's law. Pressure of the gas is inversely proportional to volume. But in mathematics, we call it the rational functions, or we call it the reciprocal functions. Or in mathematics, how we can represent this? P inversely proportional to, we have to remain general, right? So we can write it f of x equals to 1 by x. Okay, but this is the rational function, right? We cannot call this function as a polynomial function. We cannot call it as a polynomial function. Why we cannot call it a polynomial function? Because whenever we replace this x by 0, we get 1 divided by 0. So what is 1 divided by 0? 1 divided by 0 is undefined. 1 divided by 0 is undefined. So what does that mean graphically? Graphically, we can say that whenever there's a point, there's 0. At 0, we get discontinuity. Graphically, we can say that undefined means that graphically there's a point of discontinuity, right? At this point, we get point of discontinuity. So what type of discontinuity is this? This we call jump discontinuity, right? This we call it jump discontinuity. So in this graph, it can be clearly seen that f of x equals to 1 by x is discontinuous at 0, right? And this is not the polynomial function, it is the rational. We can call it a rational function. And from here, we can also, it can be clearly seen that x raised power minus 1. Here, the exponent over the x is minus 1. Exponent is minus 1. It means that it is not, as far as the definition of the polynomials are concerned, it can't be a polynomial function, right? We can call it a rational function. Now we have another graph of the function, that is the absolute, is the most important graph of the function, that we call absolute value function. Absolute value function is it is used to find the distances from the origin, and it is mathematically it is represented by f of x equals to mod x. Okay, so this is the domain set. Okay, this is the graph of the absolute value function. But this absolute value function is it is not a polynomial function. It is not a polynomial function. We cannot call it polynomial function. We can simply call it an absolute value function. But this absolute value function, it is continuous. How this continuous? Let us suppose we start from this point. We go on, and we reach there, and we reach here from point A to point B. So from point A to point B, so have we noticed that there is necessary to take the pen, to lift the pen off the board, to lift the marker off the board, to draw the graph of, to complete the graph of this function? No. So it means that the absolute value function, graphically, absolute value function, we can say that graphically, absolute value function is continuous. It is continuous. But what about differentiability? What about differentiability? It is not differentiable. Let us focus at the origin here. Okay, here we have choices here. Differentiability implies that the graphically it implies that this slope of the tangent line. So we can draw the tangent line in this way. We can draw it in this way. We can draw also the tangent line in this way, slope of the tangent line. So it means that direction of the direction of the tangent line, it changes. We can draw the tangent lines whatever manner we want. But this was not the case here in this, right? But here the direction of the tangent line, it changes. It means that the slope of the tangent line is not defined at origin in the absolute value function, when it comes to absolute value function. So from this we can conclude that the absolute value functions are continuous, but they are not differentiable, right? But they are not differentiable. So from this we can conclude that, as far as our topic was concerned, that why can't polynomial functions have fractional or negative degree, right? Why can't it be fractional? Why can't the polynomial functions have fractional or negative degree? Because there's a reason. We want polynomial functions to be continuous. We want polynomial functions to be differentiable, because polynomial functions are everywhere continuous, because polynomial functions are everywhere differentiable. That's why the degree of polynomial function can't be fraction or can't be negative number. As we have seen here, if x is in denominator, or we can write it x raised to the power minus 1. Whenever x is in denominator, here in place of this, whenever we replace this x by 0, we get jump discontinuity. So from this we can conclude that this is one of the examples that why negative exponents are not allowed in polynomials. So I hope you have understood this. See you in the next session. Fi amanillah.